Right. So before going to session, I will introduce myself. So this is Vijay Rane. I'm a Prime Minister Research Fellow in the IIT Delhi and the University of Queensland as well. And I am here working in Brisbane in the Center for Organic Photonics and Electronics, which is affiliated to the University of Queensland. So we'll here to discuss the problem based on the topic stereochemistry, the course which is taught by the Professor Amit Basak on the NPTEL platform. And we are going to the cover the problem based on the week 8 topics as we have already discussed. So we'll go for the first problem. So the first problem is predict the major stereoisomer X form in the following reaction. So they have given a reaction and we have to assign the stereochemistry for the product. So before going to the stereochemistry, does anyone have any clue which type of this reaction is? So this reaction is the addition of the nucleophile. This PHLI is stand for the phenyl ring with the negative charge and the lithium ion with the positive charge. Uh, and how this will be prepared? This is the uh, carbon ion form. You can say it as a nucleophile and the this phenyl ring which attacks to the carbonyl carbon through the uh, carbon. So it forms a new carbon-carbon bond by addition, a nucleophilic addition of this phenyl ion across this carbonyl carbon and to get the product which is like this. This is the intermediate and this is, let's say, I will review it as R and this is pH. So this O minus and lithium and after this H3O plus which stand for the workup of the reaction. I mean after completion of reaction we just generally treat the reaction with the water and so we get the just to quench the phenyl lithium and excessive phenyl lithium as well as this uh, intermediate form. So when we treat this with the water after completion of reaction, so it will get the product which is like this OH, this phenyl and this R group, which is this entirely referred as R group. So this is the reaction. So we have specific starting material with the specific R configuration they have given. So we'll draw first the compound with the R configuration and then we'll perform the reaction by taking the stereochemistry in the consideration. So I will just put it in the right. So if I draw this carbon carbon, which is let's say first, so the first carbon carbon will be like this, which is a carbonyl carbon, right? So this will be a carbon which has the methyl group attached. So methyl group, I will write it in this fashion. And the methyl group is here. And the backside carbon atom, which has the three group, which is first one is ethyl, hydroxy, and the pH. Let's say if I draw the hydroxy group here, and now where will be the ethyl and pH. So we have to maintain uh, R configuration. So where will be the position of the phenyl and ethyl group? So either it here the phenyl or ethyl. So first of all, we need to check the stereochemistry. Let's say if I write a phenyl group in the downside, so we'll see what will be the configuration first. So phenyl will be here, let's say. So the how the numbering will be for the backside carbon atom. Let's have a expanded structure here. The numbering will be the like this, right? One, this carbon will be two, and this will be three, right? So here it will be one, this one is two, and this one is three. So one, two, three. This is S configuration, right? Anti-clockwise, so it's yes. So we have to just we'll just alter change the group, so we'll get the structure with the R configuration. So I will drop pH here instead of here, and then ethyl group will be here, right? So this is how we can write the structure. And now we'll do the attack of the nucleophile. But see here what will happen. This it is a lithium ion, right? And so in the comment, it's not oxygen. I'm not giving the numbering to the oxygen. Sorry, it's to carbonyl carbon. That's what carbon carbon will be two, and this will be three, right? So one, two, three. I'm considering this carbon carbon as a two. Oxygen will get first. Carbon carbon will get the second, and the phenyl group will be get third priority. So this is above the plane, right? It is front side, right? If you just expand the structure, so it will be like this. So the carbon atom which has the carbon group, which has the second priority here. So the first, second, which is above, and this third, which is again in the plane. So first, second, third, it is S, right? And fourth priority group is that time we have draw. We'll just again show. I will show how I have assigned the. Initially, I have draw pH here. That time, the numbering will be hydroxyl group has the first, the carbon carbon will have the second, and the phenyl will have third, right? So one, two, three, it's S compression. If I see this and this phenyl is in the same plane, and the carbon carbon which is above the plane, then how it will be? It's like this way, right? I mean, the oxygen hydroxy and the phenyl will be in the same plane. This carbon carbon will be the above the plane, so it has the S compression. One, two, three. It is anti-clockwise, so S compression. So I will just alter change the phenyl. Initially, I will just keep the phenyl here, and now you can see it is perfect, right? What are the comments? I'll just check the chat box. Fourth priority will go on the dash wedge, fourth on the dash wedge. Dash wedge. Uh, I'm not getting exactly what you want to say. Hmm. All right, we'll solve this one. So we'll discuss this again. So what I have did, I have just draw this structure in this fashion. So I can, the last pair will be on the dash wedge. Here I have not draw any wedge or any bond. See how this structure will be. This is the front carbon carbon, right? And this hydroxy in the plane. And let's say this ethyl. Now I will show directly the exact structure. This ethyl above the plane. This phenyl will be below the plane. Now you check. Now you can get the better idea which how I have given the numbering. All right. So we will convert that product in this form after performing the reaction on this intermediate. We'll convert that product in such form. So if you see here, I will just give the numbering. Let's say if I just saw from this side, that is from the direction of the ethyl. So how it I will be one, two, and three. This is S compression, which is changes to R because we are giving numbering to from the uh, side of ethyl, right? Which is so this is R compression, and I have just converted this product. If you have confusion, I will just draw in some different fashion. Mm, This is the front carbon atom, which has a carbonyl group, and again the methyl one, right? And now I will just draw this hydroxy just beyond. Now I will draw ethyl here and pH here, right? So I have just see hydroxy was here also in the plane. So I have kept it in the plane of this carbonyl. And ethoxy, if I see from this side, how it will be? It will be on ethoxy, will be on right hand side, right? So I have kept it on as it is right hand side, and this one kept on as it is left hand side. So you can imagine now. And this because of this lithium, this will be the chelation will be happen like this in this fashion. And the nucleophile which is attacked from the side of the small group. So in the phenyl and the ethyl, which is small group? Can anyone guess? You can paste it in the chat box so I can. So the bulkiness of the phenyl and the ethyl, which is bulky? So the bulky will be the phenyl. So this is small group and this is large group in these two, if I compare both these two groups, right? So the phenyl, negative charge phenyl anion, from which direction it attacks? This phenyl. So sorry, the phenyl should be the same with the lithiated, right? So lithium, and let's say I have draw here phenyl. This negative charge phenyl attack from this direction, which is direction of the ethyl, and this hydroxy will go to the that direction. So how it will be? This is ethyl. Uh, Sorry, this is phenyl, right? So this is front carmatum, which I am drawing now, and this O minus will be, see if it attack it from this side. So how it will be? This will pull somewhat this direction, right? To avoid any steric strain. And this CH3. This is the front carbon atom, and the back carbon atom will be as it is, which has the hydroxy group, another ethyl, and another pH. So this is the answer. After this one, it just convert O minus will convert it into hydroxy. So you can. So this is the, sorry, this is ethyl and this is phenyl. So this is the product, and you just compare from this one which is the correct product. So let me convert this product in such form like this. So if I just pull the product, just try to convert this product. So in all options, what are the, all right, both, they have both the center will be the symmetrical, right? In this one, symmetrical in the sense have the same group like hydroxy, phenyl, and methyl. So in the product also, no, sorry, here it will be the methyl. So the methyl side is our product form. So methyl, we have to look at this product, this side. First of all, check which option has the R configuration of this starting react chiral center, this red one. So let's say 1, 2, sorry, 1, 2, and 3. It has R configuration, which is yes. This is obviously wrong. It's 1, 1, 2, 3. This is, sorry, 1, 2, 3. This is S configuration, also wrong. It has 1, 2, 3. S configuration. Oh, oh, how it is. And so you can see here, we have options. So if you just give the numbering, this one, this is second, and this third. This is R, which is changes to S because this ethyl is upside. So this chiral center has the S configuration. This chiral center has the S compression, but in our starting, they have particularly mentioned the chiral center will have the R configuration. So this is obviously the wrong option. If you see the second also, the first, second, third, one, two, three, this is S. So this is also the wrong, because our the parent chiral center, it should have the R compression, right? And if I see the third option, it has first, the second, and third. That is S compression. So this is also again incorrect. So it's like a time saving. You can directly go to this option. This is the correct option, because all this starting material they have particularly mentioned, right? So the starting material should have the R compression. But if you see the products, the starting has the S compression. So these are options are incorrect. And if you look at this option, we got the correct option. That is the previous starting chiral center, which has the IR compression that we have maintained while converting the structure from this to this. It has R compression, and after the completion of the reaction, which compression we got here? Can anybody want to? So first, the second, and third, which is R. So if you see here the compression of this, sorry, absolute configuration of this chiral center and this chiral center. So the first chiral center that is originated from the starting one, which has first, second, third, which is GS changes to R. So it is correct. It has R compression, and the product, sorry, chiral center which is newly generated, which also has the first, second, third. This is S, which changes to R compression. Right. So the D option is the correct, in which the both chiral center has the R compression. So anyone have any doubt? Please let me know if you have any doubt. So we can, otherwise we can move for the next question. And you can also see the explanation in the books given. So it also given the same explanation as we have already solved. This is just a chelate model they have also shown as here. And the phenyl attack from the side of the small group, which is the ethyl obvious. And the product we got like this. And you can convert this product in this form and followed by this form. You have to make a practice of this converting, because the most of the problems you will see like this only. So you should able to convert from the Newman to Fisher to the flying waves, this kind of confirmation. So you have to make this practice. So the option D is the correct option here. All right. Any doubt here in the first question? All right. If you don't have any doubt, we'll move for the next problem. So the next problem is the correct statement related to the sodium borohydride reduction of the admantane A and B. So they have given this X is equal to the nitro and the amine, this X particularly, this X group. And we just need to do the NaBH4 reduction on this in the isopropyl alcohol. So here we have to, they have given few statements. The C is the major product from A. So the statements given, the C will be the major product from this A. A will contain nitro group, right? And the D is the major product, that is D is major product from the this X is equal to the NH2 group. So here we have to consider the effect of nitro and NH2 on the NaBH4 reduction. First of all, keep in mind the sodium, lithium plus sodium, lithium, potassium, this sort of salts or zinc, whether they involve in the chelation or not, this effect you have to consider always. So sometimes these some ions if involve in the chelation, some ion doesn't involve in the chelate formation. So here, particularly the sodium ion they have given, and sodium ion, which obviously the not able to give the involved in the chelation because of small size. So here, in case of sodium, so we have to consider only the effect of this BH4, not the effect of any positive ions. Uh, Anyone have any doubt? Uh, you are not audible. Right. So what happens? Scene attack and anti-attack that we have to consider here. What is the scene attack and anti-attack here? So I will just draw these. We'll just keep this. So if it attack, the nucleophile attack from this side. Nucleophile can also attack from this side, right? So let's say you would have the substitution this side. So this attack considered as the scene attack, and this attack considered as the anti-attack. So this you have to consider, and which is the favorable here. So here I will show you directly the explanation. In case of the electron withdrawing group substituent, that is phenyl nitro group, right? And in the case of the B, that is electron donating, that is phenyl NH2. These two substituents are for this is the A and this is the B, right? The X is equal to pH either NO2 or NH2. These two groups are there, and the percent of syn attack leading to the E isomer. Obvious, E isomers stand for the cis. You can say cis or syn. Increase as substituent X become more electron withdrawing. So whichever the electron withdrawing group, uh, the syn attack is preferred. That is, this pH nitro is electron withdrawing group. So in this case, the syn attack is major one. And when the pH NH2 is there, that time anti attack is major. So if you see here, the if you see this reaction in which when C is major, C is major for, so this is the anti-attack, right? And this is the syn attack product. This hydride minus H minus is nucleophile here. So here, this hydride you can see here is attacked from the syn side. That is, as we have seen here, when it attacks the syn, when pH NO2, that is electron withdrawing group. So electron withdrawing group here, pH NO2, and here pH NH2. So the option C is the major product in case of A. So A, that is nitro, and C is the major product. This is wrong. The B option is D is major product from A, which is nitro, and the D, that is syn attack. All right, up to here it is correct. And C is major product from the B, that is from B which is electron donating group. So they prefer anti-attack. So here anti-attack happens, and this C is major. All right, so the B statement is correct here. So you have to keep noted. So the any electron withdrawing group prefer the, Particularly in such system, always keep noted, keep remember this side. If you keep this one remember, obviously you have to apply the opposite concept for the other. So the whenever you saw the electron withdrawing group, so the for such systems you have to do the sin attack. Otherwise, if they're electron donating group, then you have to do the anti attack. So this is the option B is the correct option here, and this are obviously will be the incorrect option. So this is the here just the concept is the electron withdrawing group. You have to keep noted this one. This is some sort of informative type question. And yes, this there are some explanation given. This is because of the Planck's hypothesis on the electron donation from C3 to C10 and C1 to C10 sigma bond will be dominated increasingly with for the withdrawing substituent. So let's give the numbering 1, 2, 3, 4. 5, 6, 7, 8, 9. I don't think the numbering which we have given here it is correct. So just look at the numbering, how the numbering for this particular this type of system will be given. So this is the effect of the Planck's hypothesis. So keep noted. Probably sometime the MCQ will may also came from the such topics. So here you can find the numbering. So the 1, 2, 3, 1, 2, 3, 4, 5, 6, like this in this manner. The next question is the identify correct statement in the given reaction and the reaction of the lithium aluminum hydride uh, they have given, and particularly it's kind of reduction reaction. Here also the nucleophile is hydride ion and lithium ion. Keep noted this lithium involved in the chelation. So here, all right. So we have to perform the nucleophilic addition reaction on this carbonyl carbon here. So I will just directly go to the options here because this is the kind of just as we have already solved this one question, right? Question number one, the same as this one. So just draw the uh, what we can say the front the carbonyl carbon, and first of all we have to draw this one front carbon. The backside carbon will be the carbon with the carbonyl group, right? This methyl. And as we have seen here, the reagents are the lithium aluminum hydride as well as the AlOAr3. So lithium as well as the aluminum, this cationic salt always involved in the chelate formation. Lithium, aluminum, zinc, particularly we will find the example based on this three predominantly. The potassium, sodium, they generally don't involve in the chelation. So this point you have to keep remember. And here, just draw the, let's say I have drawn the Al which involve in the chelation here, and which form
Electrophilic reduction.
yes, it's a reduction reaction, obviously. So the here
Redoxy aluminum complex is formed there.
Yeah. So these are the two possibilities. Either aluminum complex from this side, or it may from the opposite side, right? Here it's just rotation of this bond. I have shifted this side. Let's just rotate in this side, and let's taken the hydrogen, the methyl, and this CMe3, and carbon kept as it is. So Al complex. Either Al complex will be from these are the two main possibilities. This is and this one. So you can see here, if it is from the Al complex in this fashion, this CMe3, which is bulky group, here there will be a lot of steric interaction. But in this one, there is very less steric interaction will be takes place, and that's why this 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 kind of intermediate will be the most favored intermediate here, right? And just the nucleophilic addition, as you know, it's will be takes place from the side of the large group, particularly here. It's a Falkin Un model, that is the difference between the Falkin Un model and the Cramps model that we have to remember. In Cramps model, we generally draw a carbon like this, let's say. Sorry. Let's say we'll draw the carbon in this fashion, and the three groups we'll draw like this, and let's say a small, medium, or the medium large, any group like this, depend on this, and we attack from the side of the small group. In the chelate model, what we do? In the chelate model, we'll keep this oxygen like this, and the chelating group another, let's say hydrogen bonding, let's see it's hydroxy group in this fashion. See the front carbon atom, and the remaining two carbon atom will be two groups from the backside carbon atom will be like this. And here small, medium, whichever the small group, small, medium, or small, large, whatever it is, whichever the small group, we attack from that side nucleophile. This is the chelate, this is the cramps, and this is the Falcon model. In Falcon model, what we generally do, we keep either uh, we have to keep the small group in the 90-degree right here, and small or large. There are two options. We can keep the small group and the large group on the 90-degree, and we have to see the stability of this, whichever the complex which is getting formed. So if we draw the both options, and if it check the possibility, in this possibility there is most favored, we can see the stable conformation here. There is no any steric interaction with the bulky this Lewis acid group, and so the hydride minus can smoothly attack from the backside of this carbon, and we get a product in which this we can just convert that one into the Fisher projection and followed by the our desired product. So I think options are also in the Fisher projection formula, so you can directly select the correct option here. You just see the whichever the whether it is R or S. The same for the lower side as well. Yes, or we just give the numbering from for these two chiral center and check among whichever it has the perfect what we can say absolute configuration. So this is just repetition of the first question. Only here different model we have used. So any doubt here? You can easily get the option from here, which is the correct option. I will just show you 1, 2, 3, which is R
Valid
compression.
method,
So,
but method to predict.
so it has the R compression here, and for this one, 1, 2, 3. Sorry, R changes to yes. Yes and R. So you can see here which has the S and R option. 1, 2, 3, which is R changes to yes. 1, 2, 3. R changed to yes, 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 yes. This is wrong. 1, 2, 3. Yes, changed to R. So this is also wrong. We need yes and R, right? Yes and R. So it has first center has R calculation. So this is also wrong. This has first, second, third, which is S. The first, second, third, first, second, third, S, which has the SS. Let me check here. Oh, sorry. One, sorry, I did mistake here. 1, 2, 3. This is S changes to R. Oh, this is also correct, right? Oh, sorry, something happened here. It's not getting. Uh, so just give the numbering and the compression should be the same S and here 1, 2, 3, which is R, which changes to S. SS, it should be SS. This group has the second priority. The upper part will have the first. So here I all did some mistake. So previously, so this should have the SS compression. So you can match here. So this has the SS compression. The C, the D has the 1, 2, 3, which is S changed to R. So this is also option incorrect. So you can neglect other option and you can select the correct option here. So here, so the E is the major product wrong. It is G, right? So here you can see here there is G written. Uh, so this is G option, and the option C is the G is the major product form in this product in this reaction, and also using the anti-Felkin model. So you can oh, I will just somehow this one is getting stuck here. So if you have any doubt, please paste it in the chat box so we can clear that out as well. Anyone have any doubt here? Right. So if you don't have any doubt, so we'll go for the next question. And so this is the question on the epoxide formation, and it's example of the plus diethyl tartarate and minus diethyl tartarate. So these are the very what you can say the simple questions, but there are some trick to solve these type of questions. So before going to solve actual question, I will just show you some trick here. I think let's say if I have some sort of this is bottom right, and this is called as bottom left. I mean, this is not a terminology. Keep in mind, this is just a trick. So if it is bottom right and bottom left, oh, but we don't have that option in that kind of, I mean, in that type. So yes, I think this concept we can't apply to particularly to solve this problem. But generally, I use this concept for the problems in the NetGate. They have a particular type of questions always that plus diethyl tartrate and minus diethyl tartrate. So here the question is like predict the Q product, and we have given the double bond which containing the someone can mute themselves. Mute. I just muted him. Yeah. So it's epoxide formation using the diethyl tartarate and third butoxyhydroperoxide. And there are four options they have given. So you have to identify which is the correct option. So I will show the model here. So the model is like, let's say if you have the group in this fashion and it has the minus diethyl tartrate, so it attacks always from the upper side, that is beta phase. Beta stand for upper, right? So don't be confused between the alpha and beta. So if you have the minus diethyl tartrate, it attack from the upper side, and plus diethyl tartrate which attack from the alpha phase. So this is as we have I have shown previously, it's a bottom right. So if you have the bottom right like this, and let's say if you have the bottom left, whether it's downside, upside, it doesn't matter. So any R group, anything. So it doesn't matter which R group it present here, here, or here. So just check whether it is in this fashion or in this fashion. Let's say it has a bottom right, then minus diethyl tartrate attack from the beta phase. You just keep some note like keep what you can say trick uh, bottom right and minus beta. Just keep this one. Remember, you can get entire table. Let's say what are the options? So bottom right and bottom left, right? There are two possibility. Whether your structure which has the hydroxy group, which is on the bottom right or bottom left. There are only two possibility. And let's say if you have the plus diethyl tartrate, and I will draw the minus first. If you have the minus diethyl tartrate or the plus diethyl tartrate, minus or plus. So bottom right minus beta. So bottom minus diacetyl tetrate, it's bottom right, and it gives the beta. So obviously here what will be? Here it will be the alpha. So here it is beta. So here it will be the alpha, and here it will be the beta. So you can get entire table here from this one. So you just need to keep one note. Remember, bottom right minus beta. So only keep noted this thing. So you can apply this same scenario to all other examples. So you can see some, we'll see some 2, 3 examples like this. So let's say here, whichever example that we have already given here. So see, this is our example. So here, so here you can see here, it is given the upside. Now you will may surprise how I can apply that same formula to here. So, but if you see this one, you just keep rotate this as it is, just by like this. So you can convert the structure. How you can get the structure? So if you draw the structure, it will be like this: hydroxy and hydrogen here. Opposite to the hydroxy, there will be the phenyl. Same side, there is a methyl. In this fashion, you can convert, and the hydroxy group, which is bottom right, and minus diacetyl tartrate, it will attack from the beta phase. So you can beta phase means the upper side. So where it will be where it will attack? It will attack from this side. Let's say this is the product. So you can just convert this product into the this form. So you'll get the answer. So let's say what is the options here. So again, yeah, of course, again you need to convert again to this side in this fashion to get your the to match the options, or you can also give the absolute RS computation and match with the products here. So here, which option is the correct option? Here, see here, they have just converted, they have just move this by the, let's say, just in the plane, I have not interchanged the bond position, anything. I have just rotate the structure, entire structure. So rotated entire structure and minus diacyl tartrate, which obviously attack from the beta side, and we got this option. So this is the correct option here, and which is corresponding to the option B in the options. So this option B is the correct option. So I will just make a full table here just for you. I think no need to enter make it full table. If you just keep noted, bottom right, minus and beta. So you can convert entire what you can say chart. And if you just make for the upright or up or left, then also you can able to easily identify this. So this is minus, this is plus, this is bottom right, this is bottom left, and minus diacyl tartrate, it's bottom right, it gives beta. So let's say here it is beta. So definitely on the same side, it will not be the beta, right? So if it is bottom left, it should be opposite. And if it is beta with the minus diacyl tartrate on the bottom right, there should be the alpha when we use the plus diacyl tartrate. So you can get the diagonal. So this is the just small trick you can keep remember. Keep noted this table. I have often saw there are 4-mark question on the CSIR gate NET examination as well as 2-mark question in the gate examination. And probably you may found the same exam in the same question in the upcoming your this course exam final examination. Anyone have any doubt here? Please let me know if you have any doubt in comment box. If you don't have doubt, we will move for the our next question. We'll solve a couple of question and we'll discuss general question regarding anything, whatever you want to discuss regarding the stereochemistry course. The question is identify the correct statement with respect to the asymmetric synthesis. And the first sentence given is the a reaction showing enantiomeric excess, all right, enantiomeric excess greater than 0, all right, has enantiomeric transition state. All right. So the statement is like whichever reaction, in that reaction we got let's say R and the S isomer, and we get some isomer which is in excess, that is more than 50%. So normally whichever reaction which is not stereospecific, or we can say whichever the reaction give the racemic mixture, they don't have the, they have the 50% of both R and S, right? That is whether it is dextrorotatory or levorotatory, but the both the what you can say stereoisomers are in the equal proportion. But when we got some sort of what we can say isomer which is greater than 50%, let's say it is 52%, then enantiomeric excess will be how much percent? So the enantiomeric excess will be the two, one is the 52% and another will be definitely the 48%. So this 48% cancel the specific rotation of this 48%. Therefore, 52 minus 48, which is like 4% enantiomeric excess in this case, right? So which has the enantiomeric transition state. This is the statement. The second statement is the reaction show the enantiomeric excess equal to 0 has diastereomeric transition state. Diastereomeric means, let's say, this is a example of diastereomer, E and Z. Let's say it has one A group, it has B group. So this is kind of, let's say here, it is syn type, right? Syn or cis, you can say. And some is like, these two are the diastereomers of each other. So like this, any diastereomic transition state, or there are diastereomic transition state in the, what you can say, quaternary carbons as well. I mean the carbon atom which has the four different group, that kind of. These are the sp2, that is cis and trans. These are also diastereomers of each other. This was the cause statement. The third statement is a reaction showing diastereomic excess. The DE, remember, some always they will not give this what you can say, full form. The DE stand for diastereomic excess. E stand for enantiomeric excess. So these short forms also you have to keep in mind. So the statement is the reaction showing diastereomic excess greater than 0 has diastereomic transition state. All right. And then as we have seen, the same. The last one is the reaction showing diastereomic excess greater than 0 has enantiomeric transition state. So for that, the explanation will be the, as I will just draw here, the enantiomeric uh, transition state are energetically, what you can say, degenerated, while the diastereomic are the have equal energy values. Let's say if I just draw the energy level diagram, and this is the starting material, and let's say if I convert this reaction to the product, which has the, let's say I will just give the numbering with the R compression, and also it can convert into the product B. This is product A, and which has the compression, let's say S. So for this one, let's say these two, if I draw the energy level diagram for this is starting and this is the product. So I will draw the A product. This I will draw this with the B line. Let's say starting material has the energy, certain energy, and it convert into the product, which has some transition state here, we can say. And the same for the B as well. So B also, obviously it is both from starting from the same. Which has transition state. And if you just compare the energy, so one has energy, it has some sort of energy difference. And in this case, what happened? Let's say, can anyone tell me which product here will be form a major product in this one? Let's say the transition state are like this. This is TS for beta, sorry, B product, and this is TS for A product. So can anyone comment in the chat box? So which product here form in the major amount? See, to convert a starting material to any product, it needs some sort of activation energy. And if you see the activation energy stands for the energy difference between the starting material, this energy difference. And you can clearly see here, there is some sort of energy difference present here, right? So in this case, what happened? The A isomer will be formed in the major product, and the A isomer formed in the minor, because it needs some sort of higher activation energy. But if you see the example B, so it has some sort of less transition energy required and less activation energy required, and transition state is somewhat less energetic. So that's why here B will be major product. Sorry, than the product A. That is product with the B, what we have written, C, right? S written. It has, let's say it has S compression, it has R compression. So, and it may form I can say 60%, it form a 40%. So the energy required, there is a difference between the energies, right? So this is the energy difference. So that's why the product with the S compression, or let's say the product B, is getting from in a major amount. So that's why there will be energy difference between the uh, what we can say enantiomers. So the first statement is the wrong statement. So reaction showing the showing enantiomeric excess greater than zero has enantiomeric transition state. This is the wrong statement. They have the energy enantiomeric transition state has the energy difference only. The transition states are the same. And what you have written here equal to zero has the diastereomic transition state. The reaction show the diastereomic excess greater than zero has diastereomic transition state. So the statement C said the diastereomic transition state. So diastereomic transition state greater than diastereomic excess greater than zero has diastereomic transition state. So if you see the in case of enantiomer, the enantiomer how they form, they generally form from the, let me give the example here R, and let's say here let's B group, here A group. If anything attack here, whether it attack from this side, it will get one product, let's say R. If attack from this side, we get a product which is S. So the attack of the what we can say, anything, let I will give the example of nucleophile here. Nucleophile on the product, after attacking, we got this kind of transition state, whether this attack from this side or this side. So based on this, there will be some energy difference. If there are some energy difference between the from attack from this side or this side, and when this energy difference will happen, when these adjacent groups are the chiral. So this also you have to keep in mind. If there is no chiral group adjacent, then the attack on the both side are have the equal energies. So both the product form in a equal amount, and we can get this 50-50 mixture. So this is explanation is not only for this only one problem. You can apply the same explanation for the other as well. So if I give the some previous examples, so here as we saw in the first example, so why this there is possibility of one major isomer and one minor isomer. This is because we have one group which has the chiral center. If we have a group which don't have any chiral, what we can say, chiral center, then the attack from the both sides are possible in this one. So the explanation you can apply for any kind of problem. Here also you can see this one is the chiral center, so that's why the attack from this side or attack from that side, both have some different possibilities. And based on this sort of intermediate or the what you can say the models, we can solve these questions. Can you share today's slides? Yeah, obviously I will share within me. I mean, I'll upload it after completion of this lecture. I will upload this into the, you guys have the link right for my Google Drive. I will upload there so you can access that one. The next similar problem as we have already seen first and third. This is just addition of the NaBH4, and here we have to keep the notice on the halide effect. Here the chloride is given. So I will just, instead of spending a lot of time on drawing the transition state, here the same simple problem, this methyl, which has a carbonyl group and which has a group which has the R configuration here. So let's say I will draw the group. So here I have draw let's say I have draw here a phenyl, and there will be a group which is on the dotted side, and that is lower side and above the side. So to draw the R compression, let's say if I draw the chloride here, so the first, second, and third, this compression will be the R compression, right? So the hydrogen here. So this is the product. Sorry, this is the starting one. You can see it has the R compression on this chiral center, and you have to attack the hydride minus. So you, by looking at the structure, you can also able to attack whether should attack from that side or this side. But often there is high chances of getting mistake. I mean getting the incorrect option. So we'll go with the model. So this model I will just draw here, and here it is. We have to while applying the Cramp model, we have to consider the halide. So whenever we have chloride, bromide, iodide in the molecule, that is in the carbon atom adjacent to this one. So you can see here it has the chloride one. So you have to draw very careful. So any halide adjacent to halide on adjacent carbon atom, keep away from carbonyl oxygen, sorry, away from oxygen. So we have to keep away from this oxygen. So let's I'll show you, yeah, this here in this one. So oxygen is here. So first of all, draw the chloride one here, and then based on the whichever the compression they have given R. So if we check the compression of the R here, whether phenyl will be from this side or that side. So just to maintain R compression, we need to draw the phenyl on the right hand side. So if you check the compression, 1, 2, 3, hydroxy will be first, chloride will be second, hydroxy, no, not hydroxy. This carbon will be the first. No, sorry, chloride will be the first. The carbon will be the second, and the phenyl will be third. So it's kind of R compression, right? So R complete has R compression, so that's why the phenyl will be here. And you have to draw the hydride minus obviously from the whichever side which has a small group. So just hydride attack from the side of hydrogen, and as you can see, this hydrogen here that is newly added, not this. So this hydride, and then we have converted. So does anyone have any issue of converting the Newman to Fisher? We can discuss that one as well if you have any doubt. So because it is very important to convert Newman projection to the one Newman projection to another Newman projection, or Newman projection to the Fisher projection, or from Fisher projection to the flying wedge. So if you have to convert this type of Newman projection, you just have to pull this methyl down. So I have just pulled this methyl down. Methyl. I will draw hydroxy and hydrogen as it is. And the backside carbon atom, let's say this is phenyl group, or let's say this chloride group. I have just pulled this straight away upward. So the chloride, I have just straight pulled this straight chloride, and remaining two group drawn as it is. So if you have any kind of conformation, let's say if I draw any arbitrary conformation like this, let's say in this fashion, it has COOH, it has the hydroxy, it has the methyl group, and on the back side I have some different groups. Let's say there is a bromine atom, there is a hydroxy group, and there is a methyl group, ethyl or ethyl group. So in the so this example I have, if I have to convert this example into the Fisher projection formula, so how I will be convert this one? So I will just pull this methyl directly as it is. So I have just pulled this methyl directly This methyl will be, I will draw right as it is. The COH I will draw, and the hydroxy. And the backside carbon atom, whichever group on the lower side, you can directly convert to upside. So ethyl as it is, and the keep other group as it is. That is hydroxy, which is on the right hand side. Keep it on right hand side. Bromine, which is on left hand side. Keep bromine, which is as it is on the left hand side. So you just need to rotate. Sorry, you just need to pull this to upper side, this side ethyl, and draw the left side group on the left side, right side group on the, sorry, right side group on the right side, and left side group on the left side as it is. So this is the option, sorry, answer for this question. And the option, you can see the option B is the correct option for this. So just keep in mind, there are few rules. First one is the Cram's rule. In the Cram's rules, what we do, the carbonyl carbon, let's say this is carbonyl carbon. This is just quick revision for draw the carbonyl carbon as it is, and let's draw a group in this fashion. Let's say small, medium, and large, and attack it from the side of the small group. And in the Felkin model, you have to keep the large group on the horizontal side, right? And keep medium, small group, let's say medium, small, or small, medium, whichever it is, depends upon the which composition you have to maintain, and attack from the side of the small group nucleophile. This is the Felkin. In the anti-Felkin, in the anti, you have to keep the here small group. So the small group on the horizontal side. Let's say if I just keep it on the small group here, small and medium, large, and attack it from the side of the medium group, or it not, depends on the configuration, you have to align the medium and large. These are the Cram's rule, Felkin and model, anti-Felkin, and there are other two. The chelate one, in the chelate one, you have to maintain the chelating group which is on the same side, and the other two group, that is a division, let's say small, medium, in that two, because let's say one is hydroxy, NH2, or anything like SH, this kind of stuff, whichever has the hydroxygen bonding. So they always keep on the same side of the carbonyl, and chelate form in between there. And also keep in mind, lithium, zinc, aluminum, this kind of metal only can form the chelate. The sodium, potassium, they don't form generally the chelate. Can you please again share all slides? I will share a link in the chat box. You just copy paste at the end of the session. You can keep save that link. From that link, you can download all the slides, previous slides. So these are the some models, and the polar one that we have already seen. That is the polar, means the model which can, sorry, the compound which contain the halide atom. So that called a dipolar Cram's model. So these are 4-5 models only. Never or less, if you just make all the 4 or 5 model on the one page, so you will get to know difference between the all models. So these are very, I mean, what you can say, the simple questions based on the Cram's rule and Elkin and other Chilate model on this stuff. So these all are the questions for today's. So I have also attached some more questions, but all the questions are very, I mean, the similar. So these are some questions. I will upload this PPT as well there. You can refer this question. I have also provided their options, what you can say, uh, solution in these slides. So this is all about today's session. I will just stop recording. You can stay and we'll share all the study material, whatever you want. I'll just stop here for at least recording where it is.